All right, today we are cracking open a scientific case file from all the way back in 1991. We're going to see how scientists were trying to make a supermetal even stronger. I mean, we're talking about pushing the absolute limits of what a material can do. So let me just ask you this. How do you take something that's already at the absolute peak of its game and somehow make it even better? Well, that's the exact puzzle that material scientists were trying to solve. You see, in the world of high-performance engineering, think jet engines, spacecraft, things that have to be unbelievably strong but also super lightweight, titanium alloys are the rock stars. They're the best of the best. But hey, even a rock star can use an upgrade, right?
Okay, so let's dive into the investigation. We're going to treat this just like a detective story, going deep inside the alloy itself to hunt for clues at the atomic level.
Now, the main technique they were using is something called dispersion strengthening. And honestly, the concept is pretty straightforward. You just take your main metal, in this case titanium, and you sprinkle in these tiny, super hard particles. It's exactly like how we add steel rebar to concrete to make a skyscraper strong enough to stand. Same idea, just on a microscopic scale. So, this 1991 investigation really focused on two secret ingredients, or our two main suspects, if you will. First up, boron. It reacts with titanium to create these tiny ceramic reinforcements, and then you have erbium, which is really clever. It actually grabs stray oxygen atoms that are already inside the metal to form super tough oxide particles.
The game plan was pretty simple on the surface. They whipped up several titanium alloys, added either the boron or the erbium, and then, and this is the key part, they used a technique called rapid solidification. You can basically think of it as flash freezing the molten metal. This step is absolutely crucial because it traps those little strengthening particles in a really fine, uniform way. And then, it was time to put the results under the microscope.
And we're not talking about your high school science class microscope here. No way. They used a transmission electron microscope, a TEM. This thing is an absolute beast. It's powerful enough to let you see the patterns and structures formed by individual atoms. This is our magnifying glass for the entire investigation.
All right, let's open up our first case file, the boron blueprint. What exactly is going on when you add this element into the mix?
So the first big clue they found was that boron is a bit of a chameleon. It doesn't act the same way every time. See, in alloys that had more titanium, it formed these tiny needle-shaped particles. But in alloys with more aluminum, it formed these blockier hexagonal particles. So the main recipe of the alloy actually changes the shape of the reinforcements. How cool is that?
Okay, let's zoom in on those needles for a second. The scientists called them semi-coherent, and that's a really important term here. It basically means the atomic structure of that tiny needle is trying its best to perfectly line up with the atomic structure of the titanium all around it. It's trying to fit in as perfectly as it can.
And this is where it gets really, really cool. The researchers saw, and I'm quoting directly from their 1991 paper, a highly faulted structure. Now that sounds bad, doesn't it? A fault? An error? But it turns out that's actually its secret weapon.
Get this, that fault isn't a mistake at all. It's a planned imperfection. It's this tiny repeating structural flaw that actually lets the boron needle relieve stress and light up even better with the titanium. It's like a clever little atomic hack that makes the whole thing stronger. It's a feature, not a bug.
Okay, now let's move on to our second case file and see what's going on there. The erbium enigma. And trust me, this story has a pretty surprising twist.
So when you add erbium, it does its thing, scavenging oxygen and forming these cute little spherical particles of erbium oxide. Seems nice and simple, right? Well, not so fast.
The first little wrinkle they found had to do with size. At 800 degrees Celsius, the really tiny particles, we're talking smaller than 50 nanometers, were coherent. They fit in great. But as soon as they grew bigger than that, they became incoherent. Their atomic structure just didn't line up anymore.
But here's where the real mystery kicks in. The researchers decided, hey, what happens if we push the temperature even higher? And this is where the story gets really weird. And what they found was wild. At 800 degrees, you get those standard little spheres we talked about. But when they cranked the heat all the way up to 1000 degrees Celsius, those spheres vanished. And in their place, something entirely new and unexpected started to form.
They had discovered a brand new mystery phase. This thing was a total curveball. Instead of just erbium and oxygen, this new particle also had titanium in it. And instead of a sphere, it was a flat, faceted platelet. But most importantly, it was fully coherent. It lined up perfectly with everything around it. This was a completely different behavior that only showed up under extreme heat.
So after digging through all the evidence on both boron and erbium, what was the final verdict from our 1991 scientific detectives?
Okay, let's break it down side by side. You've got boron, which turned out to be really predictable. It formed its needles or blocks, and crucially, they stayed that way even when things got super hot. Erbium, though, was more of a shapeshifter. It formed spheres at lower temps, but then completely transformed into something else above 1,000 degrees Celsius.
So the conclusion was crystal clear. Boron was the more robust, more reliable strengthener, especially if you need something to work in a high-temperature environment like a jet engine. Erbium worked, for sure, but that unpredictable transformation made it much better suited for a narrower, lower-temperature job.
And what's just amazing to remember is that all of this incredibly detailed, atomic-level detective work was being done back in 1991. This was foundational stuff that really helped pave the way for the incredible advanced materials we have today.
Which, of course, leaves us with one last big thought. This research gave us a blueprint for how to engineer materials literally atom by atom. So the question is, now, more than 3 decades later, where have these incredible discoveries actually taken us? And what new mysteries are we solving inside materials today? Thanks for tuning in.